When we talk of classical physics, in general, what comes to our mind are either the laws of geometry framed by Euclid in his famous Elements, the laws of classical mechanics framed by Isaac Newton, or the electricity and magnetism done by James Clerk Maxwell, as well as the Rutherford or Bohr's atomic model, or even taken up to some extent Einstein's special and general theory of relativity. But I can tell you the original or the true nature of classical physics is much more deeper and philosophical than what you think are just momentum, force, vectors, and what comes in general to our mind. In this video, I'm going to talk about the true nature of classical physics, and I can promise you that by the end of this video, you will get a totally different kind of an understanding on the nature and the understanding of classical physics, which is much more profound, much more deeper, and much more philosophical, which will not only help you to understand classical physics and do the mathematics, but you will understand the other branches of physics much more better. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this video where we are striving to understand the deep nature of classical physics. So first, what we look into this, in general, what do we mean by what is classical physics? Now, if you see that when we start talking of classical physics, in general, what comes to our mind are either the pioneer work of Aristotle that significantly influenced Western thought and science, the groundbreaking contributions in geometry done by Archimedes and Euclid's Elements, Johannes Kepler's laws of planetary motion, and Galileo Galilei, a key figure in the scientific revolution who made significant contributions to physics and astronomy. We also find Sir Isaac Newton's laws of motion and the law of universal gravitation, Michael Faraday's pioneering work in electromagnetism, James Clerk Maxwell's equations uniting electricity and magnetism into a single framework, Bohr's model of atom, and Einstein's groundbreaking theories of relativity, revolutionizing our understanding of space, time, and gravity. So in general, when we talk about classical physics, the question is that classical physics does not refer to the classical antiquity which we generally think in our mind. So the question is that are we talking of an old era, an era when something is really not modern, or are we talking about the scientific revolutions which happened in the 20th century or something else? Well, we would look into that, what do we mean by classical, and then we will go deep in understanding the philosophy of classical physics and why it is very important to all of us. From this definition, we can understand that if a ball is rolling down an inclined plane, so the laws of motion, or it can be a pendulum swinging to and fro, and also the celestial mechanics, which involves the revolution of the celestial bodies around a massive body, or uniting electricity and magnetism together, or electricity and magnetism taken in a different way. But I can tell you it is not so. So what I'm trying to make you a point is that classical physics is much more deeper than this, and there is a nature of classical physics, and this nature is the pivotal force that creates, drives, and formulates all laws of this universe. Let us understand that the basic idea of today's video is not to go deep into the mathematics, differential, integral calculus, but to understand the deep true philosophical meaning of classical physics, so that the understanding of other areas of physics as well as this part comes something very important. So you're going to explore something really new, and I am going to tell you what we call the nature of classical physics coming into the next part of our video. So the term classical in general physics refers to something or the formulas or mathematics or science before the advent of quantum mechanics. So classical physics in general would include Newton's law equations for the motions of particles, Maxwell and Faraday's theory of electromagnetism, and obviously Einstein's general theory and special theory of relativity. So from here what we see is that it is a set of principles and rules, and there is definitely a very strong underlying logic, and these logic and all those principles actually governs all the phenomena that we see around us. But that is not all. We started talking in this video about the true nature of classical physics. Is it something which we are missing to discover the true nature of classical physics? Let us find it out in the next part of our video. Now you see that human beings, we all have a nature, and classical physics also do have a nature. So what does the study of human nature or human beings do helps us? It helps us to get a better relationship. It helps us to enhance the community. It also helps us to understand the richer perspective of the world. So understanding the nature of human being can help us to understand who is angry, who is soft, who gets happy, who gets a little bit melancholic. So we understand the nature of human being in order to understand human being and thereby get a better communication and make the world a better place to live. Now, when we talk about the nature of classical physics, it also helps us to understand the philosophy of physics, not only classical but other very well. And I'm going to talk more on that. It also helps us to learn other branches of science. And remember that classical physics also gives us a better understanding of what is called the quantum world. So learning other branches of science means the other areas which are not very classical in nature, and it would help to understand the very small, that is the quantum world. So the more we understand about the very big on a macroscopic scale, the more we understand the very small. The more we understand about the precise deterministic behavior of physics and the things that go around us, the more we learn about what is called uncertainty or probability. And the more we learn about the classical nature of classical physics, the more we learn about the relativistic part. This is what we are going to explore, that how the big turns to the small, how the definite becomes easy for us to understand the uncertain, and the classical physics, how it helps us to understand relativistic physics much more better. But before that, I would like to explore something very interesting coming up into the next part of a video, a hypothetical understanding which is called the Laplace demon. Now, when we talk about Laplace demon, what do we mean about that? And this is very central and very philosophical in our understanding the nature of our mother nature. So in the history of science, you see Laplace demon was a notable publication which was basically depending on causal determinism on a scientific basis, designed by Pierre-Simon Laplace in 1814. And according to determinism, if someone, for example, a demon, knows the precise location and momentum of every atom in the universe, their past and future values for any given time are entailed, they can be calculated from the laws of classical mechanics. So this was a kind of a hypothetical understanding. So here you see a funny demon, and this demon actually knows precisely the location, momentum of everything. And it says that then the laws of mechanics or the laws of mechanics in the future can be calculated out of that. Now, Laplace demon actually was articulated and framed in this type of a line. So if you read this entire, statement of what Laplace made during 1814, what becomes most important are those which I have made it in red. First is that there is a hypothetical intellect which at a certain moment would know all forces that set nature in motion. That means time is very important, a certain moment. The next thing which becomes important is that if this intellect were also vast enough to submit this data to analysis, that means that that intellect has to collect at a certain moment and submit it to a data analysis. And also what is important is that this would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. That means we can get a hint of what we today call as a grand unified theory or a theory of everything, where this intellect is putting those data into analysis and trying to get one single formula which would embrace everything. Now, this is all which is given in our English text, but can we have a kind of a better understanding of Laplace demon in a pictorial form? Let us look into the next part of the video. So here is our demon, and these are the fundamental forces of nature: gravity, strong force, weak force, electromagnetism, as well as the atoms and molecules. Now, Laplace's demon hypothetically perceives that there should be one area which is very important, that all all those things should go into the right hand side part, which is called the data analysis. So if I take all those things and I put into something which is called the data analysis, then from here we get a single formula. If you go back to the previous few seconds of this video, I have just mentioned that Laplace told that there should be one single formula, and this single formula will be able to predict not only that part but also something which is very big, just like a black hole, or very small, which are like the quarks or the anti-quarks. But quarks was not discovered during that time, so I have given an example. So putting all those data into data analysis, getting a single formula, and through that formula we will get to know and predict what is the very big as well as the very small. And not only that, the future, as Laplace told, the future, just like the past, would be present before its eyes. Now, you might think this is something very odd, very foolish, but this is the culmination of the thought of getting a grand unified theory, or a theory of everything. And this Laplace demon is so very important in understanding the nature of classical physics, as we will explore. So this is a kind of a pictorial idea, a pictorial description to show you that what Laplace's demon actually meant to get a single formula, and the future would be just like the past in front of our eyes. So the Laplace's demon in classical physics makes a very important contribution. The contribution is that if you know everything about a system at some instant of time, you may also know the equations that govern how the system changes or how the system would behave in the coming future. Now, I have highlighted this point, instant of time, because I want to now take an exception. Now let us suppose that this demon does not know something, or the momentum force or whatever we call, at an instant of time, and it is spread over a certain time. I am taking it as an exception. What if that particular event doesn't happen over a instant of time but over a range of time, and it is not also something which is reversible or reversible? Let us find it out in the next part of the video. So what if it is not an instant of time and spread over a wide range? So instantly, you see, when we talk of a moment of time, we mean locality of physics, which becomes what is called non-locality of physics. We also get into something which we already know, which is called quantum entanglement, and certain physical phenomena can be correlated or even entangled in ways. Now, why I'm making this a point? Am I talking about quantum physics in this video? No, I am not. But why I'm talking is that now you see that if I take an exception of Laplace's demons, I would say perception of the future, which will be just in front of us eyes, we automatically find something which is not very classical, and we automatically see quantum entanglement and non-locality comes into the play. So here is a kind of a pictorial understanding of what is quantum entanglement, which you already know, and this is what is called the wave function. So here is the understanding that knowing the state of an particle can instantly tell you something about the state of the other, regardless of the distance between them. That means that this quantum entanglement, which we now call quantum entanglement, if I go back to Laplace's statement, what if we are not taking an instant of time? Immediately the concept of non-locality, etc. rises. So here is the statement: this kind of non-local behavior is not possible within the framework of classical physics, which assumes that physical interactions always propagate at a finite speed, and that the state of a system at any given time is determined only by its local history. So, as I told you, that understanding the true nature of classical physics automatically will give you a better understanding of other areas of physics, including quantum mechanics. You find it right now that this is something which is framework of it is this non-local behavior is not within the framework of classical physics, because classical physics, the interactions are always at a finite speed. Now, from here, I would like to take up a little bit more details on what we mean by local history and non-local history, coming up into the next part of our video, where I would like to give you a very quick example of what is called a spontaneous emission. Now, spontaneous emission is something which is very spontaneous. That means it will happen immediately. So if I take a quantum mechanical system which transits from an excited energy state to a lower energy state, that means it emits a very limited, a quantized amount of energy in the form of photon. And you can see spontaneous emission in the fireflies, in the neon lights, in the incandescent light bulbs, as well as in the flames. So it is something very spontaneous. So this process occurs naturally and is responsible for various real life phenomena and applications. Now, why I am taking up spontaneous emission? Because I would like to show you something very important and something which is very central, not to quantum mechanics, but to classical physics. Now, here you see that spontaneous emission is generally considered as an irreversible process. So those who are watching this video, a quick note of caution that this is not entirely true, that it is not an irreversible process. I will give you an understanding in a few minutes from time. But let us understand and assume that it is an irreversible process. So what it does mean that it cannot be absorbed by the atom that emitted it. For example, at the energy level of E2, if an atom emits, for example, a photon, then it can go back to E1 state, that is the ground state. But from going back from E1 to E2 is something which is not allowed. This is the concept of what is called spontaneous emission. So you see that once the spontaneous emission has taken place, the system moves to a lower energy state and the emitted photon carries the energy difference. But the problem is that the system doesn't return to its original excited state after the emission. And we will soon see that this is the difference between quantum physics and classical physics, because it comes again from the true nature of classical physics. So it is not going back to its original state. Now, you might have a question that then what is a reversible process? And the example is right in front of you, but it's called a reversible isothermal expansion. And we know what is a reversible isothermal expansion. So a process is reversible, meaning that the system can be brought back to its initial state by reversing the state and the process. Now let us look into not only this idea that why it cannot go back to its atomic original state and why it is called an irreversible process. So here is the atom, the quantum mechanical state, and here is the photon, which is denoted by the Greek letter gamma. Now once it is emitted, you see there are an infinite amount of possibilities. So taken into account case 1, how will this photon go back to its original state? Because there is a question of infinity which arises in terms of emission of the photon. So going back is very difficult because there are an infinite amount of possibilities. Even if the photon is absorbed, the second case number 2, it is not guaranteed to return to its original state. Why? Because the photon may have lost some energy during its journey. So from E2 to E1, going back again becomes very, very difficult because the photon might have lost some amount of energy, so it cannot go back. This is case number 2. Now let us take another. So going back to E2 or the original state is not possible. Let us take another example, which is a third case 3, that even if the photon tries to get back over here, what happens is this one. Even if the photon does manage to absorb the excited state, the reabsorption process is not instantaneous. That means if it is not instantaneous, then that becomes something which is called irreversible. The entire idea of giving the idea of spontaneous emission and why it is not going back is to tell you and make you understand this is something which is not permitted in classical physics, understanding the true nature, that's what is quantum mechanical in nature. So here it is. In a purely isolated system, remember, the combined system of the atom evolves unitarily, meaning the process is mathematically reversible. But given in certain areas, we can do the reverse. So the information about the initial excited state is still encoded in the combined system, even though atom itself is in a lower energy state. However, reabsorbing the emitted photon and reconstructing the original excited state is extremely improbable due to the photon's ability to occupy a vast number of modes in the vacuum, which I told you. So mathematically, this process, meaning the process is mathematically reversible. in a purely isolated system. But given due to the photon's ability to occupy, it becomes, extremely improbable. So here you need to also understand the true reality is this: microscopically it is reversible. If you know what I told you, the perfect knowledge of the combined system, etc. But macroscopically it appears irreversible due to information loss and the loss of energy, etc. So if you do a special setup like cavity quantum electrodynamics, etc., then you can demonstrate reversible behavior. So the basic point and idea of telling you is that we assume this to be irreversible process, but microscopically it is reversible, but macroscopically it appears to be irreversible. But given certain areas and conditions, we can reverse that process. Now, the entire idea is that spontaneous emission, being an irreversible process, is something which classical physics or Laplace's demon or the statement is something they cannot define that. So you can understand now that how the concept of quantum mechanics and entanglement and something which does not follow the speed of light becomes very evident if you understand the true nature of classical physics. So from here, what we go ahead and that we understand that what is the true nature of classical physics giving rise to quantum system. Now, when we talk of system or quantum system or classical system, what do we mean by a system? Let us look into the next part of the video. And before that, this is a system. That is what we mean that when we saw, say, the classical laws of physics are deterministic. If we can say the same thing, but with the past and future being reversed, such a system is what is called a reversible system. Now, as I told you, system, classical system, quantum system, what do we mean by system? Let us look into the next part of the video where we will take a different kind of an understanding of what is a system. Now you see the word system coming from the Greek systema and this Latin systema actually can be interactions of things. It can be as simple as a ball or it can be as complex as a universe. But the basic idea is that the whole concept is made of several parts or members or literally in sense composition. So a system in physics is a collection of objects that are actually interacting with each other. So if it is a ball which is rolling down, the motion of a ball, it helps us to study the behavior of objects in the controlled environment. So with this ball taken as an example, we can create a simple system consisting of the ball, and by studying the system, we can understand the laws of physics and even we can predict where in the future the ball will land up to. So this is called a system. The question is that it is made of composition, collection of objects, etc. So is there something which is not a part of a system, or can we call it as not a system? Let us look into the next part of the video. What is not a part of a system? Isolated elements, for example, individual elements without any connection or relationship do not form a system. Example 2, abstraction without real world counterparts. Example 3, random occurrences. There might be randomness in nature but without any discernible patterns. Number 4, groups with no identifiable structure or relationship cannot be considered as a system. Why I'm making you understand, so that you can also understand that what is a system, what is not a part of a system, and these are the most important points. Isolated elements, random occurrences, open-ended collections, abstract without real world counterparts, and lack of coherence or forming an organization. This is what is called of a system. And we just talked about what is a reversible system and what is a irreversible system. We found that spontaneous emission on a macroscopic scale is an irreversible system. So let us look a little bit deep into understanding what is a deterministic, and if it is deterministic, it has to be a reversible system, coming up in the next part of the video. So we take the simple example of a pendulum. That means in classical physics, a reversible system, if it has got this initial, then it will have a final. So if I know the velocity, motion, exact conditions of this particular pendulum when it is starting up, so that is I have written, then be returned to its exact initial state by reversing the process without leaving any trace of the process having occurred anywhere else in the universe. So a kind of a pendulum going up and down. Let us see further examples. It can be this one also, a ball bouncing on a frictionless surface. It can be a kind of an isothermal process when you blow air into the balloon, it expands and then it compresses. These are all examples of what is called a reversible process. If I talk of an isothermal expansion, then we know that as we add air more to the balloon, the volume of the gas increases. And to accommodate this volume, the pressure of the gas decreases and the gas particle have more space to move around, so they collide with the walls, etc. Very elementary physics. What is isothermal compression? When we squeeze the balloon, the volume of the gas decreases, and to maintain the temperature, the pressure of the gas increases, and the gas particles are now crammed into a smaller space, so they collide with the walls of the container more frequently, exerting more force. And I'm not going to repeat this, very elementary, which is called Boyle's law, or PV equals to constant. So these are the concepts of what is called a reversible system. And we saw now, and if you take a contrast now with the what we call spontaneous emission, etc., you see these things are missing, and that is why it is called an irreversible system. Now we need to also know what are the basic characters, I mean to say what are the striking features of a reversible system, coming up in the next part of the video. First would be deterministic. Obviously the system's evolution is governed by deterministic laws, so that the future is uniquely determined. Microscopic reversibility, very important, that when we go back, the individual particles of the systems retrace their exact paths when the process is reversed. The next most important thing is what is called no dissipation of energy. That means no energy is lost or gained during the process when it is going back. Now, if I take this picture of spontaneous emission, it is clearly telling that it cannot go back, because as you see, there is a loss of energy. There is a dissipation of energy in case of a spontaneous emission, which is not present in a classical system, and it tells among the third characteristic there should not be any loss of energy during the process of reversal, which spontaneous emission does. So 1, 2, 3, deterministic, microscopic, no dissipation, and another most important is what is called an isolated system. Now this tells that there is no exchange of matter or energy. Making exchange of matter and energy makes things very difficult, makes things very complicated, makes the mathematics more difficult, so that we cannot perfectly predict what is the future. So as I have written that in reality perfect isolation is difficult to achieve, but theoretically we assume that it is considered approximately reversible, because the interactions with the environments are almost negligible. Now here comes a very important fact, that when we talk of the isolated system, the systems which are not interacting, idealized perfect condition, then we get another concept of physics which is called linearized gravity. Now this is something which is related to general relativity, but I would like to give you a comparison between an isolated system and the concept of linearized gravity. There is no matter exchange, isolation, etc. So what happens is that in a linearized gravity, we assume that the gravitational field is so weak, right, that the background space-time metric tensor and other related mathematical tools become flat, and they becomes very easy to understand as a small perturbation around a flat metric. Here also you see, by expanding the Einstein field equation around this kind of a metric, we get a kind of a linear equation instead of the difficult partial, differential, non-linear equations, and it makes the mathematics much more easier, and we can get a kind of an analytical solution in many cases. So again, this proves that classical general theory of relativity is a classical system, because linearized gravity is perceived, or it is calculated based on some kind of an fundamental understanding of an isolated system, because isolated system is also where there is no exchange of matter, energy, and so on. And gravitational field, the huge difficult Einstein's field equations, how can we do that if things starts to interact? And that is why you see I have spoken in my previous videos about what is called a Schwarzschild black hole, because that is an ideally spherical, non-chargeable, non-rotating black hole where the isolation helps us to do a better mathematical understanding. So nonlinear equations actually gives rises to difficulty to solve them, and taking certain conditions and variable, we reduce it from nonlinear to linear, we get a linearized gravity, and the solutions to weak field equations becomes the weak field metric. So we get different kinds of metric like the Kerr metric, the Schwarzschild metric, and the Friedman, Lemma, Robertson, Walker metric, which I am definitely going not to talk. But linearized gravity and isolation are closely related to each other, and that is how we perceive, as I told you, the true nature of classical physics gives us a better understanding of many other branches of science. But still there is a question. The question is that how can studying a simply closed system like, say for example, pendulums, etc., helps us grasp the complex concept of determinism and reversibility in the universe. And we know all of these are evolving through time. So how do we do that? Let us find in the next part of our video, and here we will understand what is called a dynamical system. Now, dynamical system is something, as you understand, it is very dynamic. That means it is a mathematical framework which changes over time. You can talk and think it is as a recipe for describing the evolution of system, and it tells how each element of the system influences the other. So there are three important parts of a dynamical system. One very important which we are going to learn, which is called a state space, and this is a mathematical space that represents all possible states of that system. Now hold on, this state space will be something very interesting when you explore what is called a quantum state. But before coming to all those things like quantum state and state space, etc., what we need to understand is that this is an ingredient, important understanding of classical physics, state space. Right? So it is a state, it is a condition which actually represents all possible states in the system. Next is obviously time, because dynamical system means that there should be a tracking system which will tell that how the system is evolving. That means how the system evolves smoothly or whether there are any jumps or not. And there should be something which is called the evolution rule. That means this will tell you how the state of the system changes over time. For the pendulum, the evolution rel would be set to equations and others will be something different. So first we will start to understand what is called a state space by taking a very, very simple example of a coin which has got only one state. What is that? Let us look into the next part of our video. First, I would like to define in a very simple English what is called space of states. And this is what is called the collection of all states occupied by a system. Is a space of states, or simply it is a state space. The state space, remember, it is something abstract. It is a mathematical set whose elements label all the possible state of the system. So in classical physics, the state of a system refers to a complete, so you understand it is a complete description of all its physical properties, etc. Now let us say, for example, I have got a coin which has got only one state, which is the head. I mean to say, it has not got a head on the tail. It is a coin which has only got a head. So what happens is that the system has only one state. So predicting the future is very easy. Nothing happens and it is only head and head and head and head. So only we get a head, and that is called a single state system, a coin which has got a head and its future is only just a head. Now you see, now we have got a head and we have got another coin which has only got a tail. Just to clear things, it is not that one coin has a head and tail. There is one coin which has got only head. There is another coin which has got only tail. And from head, if we move, we get another head and another head. If we take a tail, we get one tail, another tail and another tail. So from here what we can see is that we assume that the systems evolve smoothly. So from head we get to several heads, from tail we get to several tails. And we do not jump around, right, from this one to this one, and this is called continuous. But how can you assume that if you're going from head to tail, you are moving continuously? There can be jumps. There can be discrete jumps. And there is a term in physics which we call as stroboscopic. And what is stroboscopic? I'm going to explain it to the next part of the video. So stroboscopic effect is basically a visual phenomena that is quite different from continuous. And it is something which is in a series of short or instantaneous samples which comes. I will show you a nice animation, you will find it easier. So for example, a strobe fountain, a stream of water droplets falling at regular intervals lit with strobe light, an example of stroboscopic effect. So here you see right now. So this actually is taken from Wikipedia, which shows that the frequency of the flash. So the element appears motionless or rotating or reverse direction. So here there is a discrete jump, and it is not something which is very continuous, and this is what is called a stroboscopic. Okay, from here what we do is that this dynamical law, that is a head and a tail, so we can write this in terms of quantitative idea. So we are moving from head to tail and we are going from tail to head. So what we get from head to tail, if we move, we get H, T and a H and a T. If we start with tail, we get T, H and T and a H. And how do we write that? We write that using this Greek letter sigma. So I mean to say, we will take this as a degree of freedom. Obviously, it is moving from head to tail, so there are degrees of freedom. So what are the degrees of freedom? I will denote it by the Greek letter sigma. And when we get into this one equal to 1, that is head, and let us assume minus 1 to be a tail. So if I take this kind of an equation, sigma, n plus 1 equals to sigma n. So what does it mean? It means whatever the value of sigma at the nth step or step number n, it will have the same value for the next step. And if I take the another equation, sigma equals to n plus 1, which is equals to negative sigma of n, that means what? That means that the state flips between each step. That means there is a kind of a flipping. Now, because in each of these cases, as I saw, sigma equals to 1 and minus 1, the future behavior is completely determined by the initial state. Such laws are what are called deterministic. All the basic laws of classical physics or classical mechanics are deterministic in nature. Okay, now we have taken H and T. We can take numerous other examples, but these are pretty easy in nature. But why don't we generalize to a little bit complex system, which is this one, which is called a cube. So instead of a coin which has not got a head or a head and a tail, let us take a six-sided die where we get a kind of a 6 possible states. Again, what we are doing, again, we are generalizing so that our understanding is much better. So if we take a six-sided die, it will evolve into this kind of a system. So if I'm starting from 3, I will go from 3 to 4 to 4 to 5, and then from a 6, 6 to 1, 1 to 2. And if I plot this, it will look something like this. So this has got n plus 1 and it will go on endlessly because it has got an endless cycles. So this is an example of a 6-state system which is a cube and how it goes on and on and on. Let us look into another example, this one. So if I start from the position of 2, what I get 2 to 6 to 1 to 2 to 6 to 1 to 2 and I go on. But remember, this is something where I cannot go to 4, 5 or 3 and it has got 2 cycles. And if I start with 5, I go to 5 to 3 to 4 to 5 to 3 to 4 and I cannot go back to 1 on 2 or 3 or so. And I can have more. I can have 3 cycles from 5 to 6, 1 and 2. Then I can go from 2 to 3. So there can be numerous examples. So what we can do is that we can combine and generate several dynamical laws. However, this is just an example to show how the different states of the system evolves. Now, these are all rules which are allowed, but there are also certain rules. The Laplace's demon says that there are certain rules which are not allowed. What are the rules in physics that are not allowed and what we learn from those rules? Let us find into the next part of our video. So it is not enough that a dynamical law should be deterministic, it must also be reversible. That means that if you reverse all the arrows, the resulting law is still deterministic. That means it is to say the laws are deterministic into the past as well as in the future. And what Laplace told is that he perceived an intellect nothing could be uncertain and the future just like the past would be present before its eyes. That means the future would be also just like the past. It will be able to predict it. Let us take an example. I will take a very simple example. So yeah, the question is that can one conceive of one conceive of laws that are deterministic into the future, or we can say, can we formulate irreversible laws or reversible laws? Let us find into the next part of the video. So we take this kind of a system 1, 2 and 3, and I put an arrow. That means I'm going from 1 to 2, then from 2 to 3, and from 3 I'm going back to 2. I'm going to say this is absolutely clear. There is absolutely no problem with this present or the future. It tells where you are and where will I go. Now let us assume a hypothetical situation where I am standing here. That means I have just come, spontaneous, again that concept, that I am just at point number 2. Now if you ask me where will I go, I will obviously go to 3. And from 3 where will I come back? I will come back to 2. But if I ask you this question, where were you just before you came to 2, you don't have an answer. Because 2 does not have a past. This is what is called, so from 1 to 2 you can go back, see the animation once more. But when I come back from 2 to 1, there is no answer. And this is what is called an irreversible system. That means there is no state that leads to 1, and state 1 has no past. And this is something which is not allowed in classical physics, and it is called an irreversible system, and it is not allowed in the principles of classical physics. But this is something which is allowed on a macroscopic scale, on a quantum level, and that we demonstrated in spontaneous emission. So this is a reversible system, and if I make another system where I put the arrow from 2 back to 1, and I go from 2 to 3 and 3 back to 1. So this is a system that is not deterministic into the future. Again, now I have got a past from 2 back to 1, and I know from 2 I am going back to 3 and 3 going back to 2. But the question is that if you reverse the arrows of the above figure, I mean to say the left hand side figure, the corresponding law fails to tell where you go in the future. So now the question comes is here, that when does a diagram represent a deterministic reversible law, or you can put it in this way, can we have a formula when we can actually determine a diagram which is deterministic and reversible? Here is something very important. If every state has a single unique arrow which leads into it and an arrow leading outside of it, then it is a legal deterministic reversible law. And you can also say that there must be one arrow to tell where you are going and one arrow to tell where you came from. If you formulate a figure or a system based on this, then it is called a reversible deterministic system. Now the question also arises that we saw all 1, 2, 3, I mean to say finite systems which has got 1 state, 2 state or many. But do we have a system where it has got infinite number of states? If it is so, how do we define? Let us find into the next part of the video. So here you see, you can consider to be a rail track or a number of shops, etc. And here you see from 0 I'm going back to infinity, and from 0 I'm going towards infinity. And we already know that we use the notation small n in order to denote those discrete jumps, I mean to say time steps. Let us suppose this denote discrete time steps, and let us say uppercase N or capital N will denote the point on the track or on the road. So if I take a history of the marker would consist of a function which will be capital N of n, and it will tell you the place along the track n at every time of n. So I mean to say this capital N, as I just denoted, is going to denote the points on the track. So this function, if we design it in a very nice and simple manner, it will tell you the place along the track capital N at every point in n, and this is what is depicted in the figure. So now, because we have an arrow going into it and outside it, now if we form a kind of an equation like this, it tells that wherever you start, you will eventually go to every other point by either going to the future or tracing back to the past. And if I take this kind of a formula, it states that if you start at an odd value of n, say 3, right, you will never get to an even value, and vice versa. So these are the laws which states that not only a finite, we can also have an infinite number of states, and this is how we define them. Now from this finite and infinite, we come up to the last part of our video, which is very important, and it is called conservation of laws. Yes, you have guessed it rightly. The law of energy, the law of conservation of momentum, all crops up from this kind of a basic philosophical understanding of the classical physics, coming into the next part of the video. So when a state space, we already know what is a state space is, right, is separated into several cycles. So what happened? The system remains in whatever cycle it started in. Or we can say that each cycle has its own dynamical rule, and they are all part of the same state space because they describe the same dynamical system. Let us look into this kind of a figure. Now here you see on the left hand side, each state, states 1 and 2, belongs to its own cycle because 1 is going back to 1, 2 is going back to 2, while 3 and 4 are just going up and down. Similarly, if I now define C as conservation, and I define plus 1 as C equals to plus 1, and again I define minus 1, C equals to minus 1, and something between 0 to 0 or 3 to 4 as C equals to 0, you will see whatever the value of C, it remains the same for all time. Why? Because the dynamical law does not allow any jump from one cycle to another, and this means what? It means that C is actually conserved. So the concept of the conservation is a state space where the I would say the state belongs either to that state, it is cycling back to that, or it is going back and forth, and quantitatively if we define any variable, it would remain the same. Now these are all laws of physics where we try to define, understand the true nature of a reversible or reversible of a deterministic classical system, and from here we see how the quantum system evolves. But let us also understand that we have limitations in terms of our measurement. We cannot always define terms very easily. Now what I am trying to tell is that Laplace's demon, or what Laplace thought, may have been too over optimistic about how predictable the world of classical physics would be. Now these type of predictions would have agreed that predicting the future would require a perfect rigorous knowledge of the dynamical laws governing the world, as well as a tremendous computing power. Because if you read the original line of Laplace, he told that intellect vast enough to submit these data to analysis. The question is that how will we get this vast enough intellect? Right. There is another element that Laplace or during that time has been underestimated, that is the ability for human beings to know the initial conditions with almost perfect precision. Now in order to do that, I will take a very hypothetical example. Let us take a die, right? I have taken this from this website, so I have cited that. So let us take this die and let us assume that this die has got millions of faces. Question is that how will we develop a dynamical law with so many different faces? And you see, in the reality, things are even worse, because the space of states is not only a huge number of points, but it is continuously and it is infinite. So I mean to say, even if we label a collection of real numbers such as this dice or any coordinates, etc., real numbers are actually so dense that every one of them is arbitrarily close to another, which leads to infinite number of neighbors. Each of them are arbitrarily close, and this will revolve and get an idea of infinite number. So this is actually which is called the ability to distinguish the neighboring values of this number is something which is called a resolving power, and in principle we cannot know the initial conditions with infinite precision. So here it is, the ability to distinguish the neighboring values of these numbers is the resolving power of any experiment, and this is something which we absolutely have got a limitation. So what we deduce from here is that we cannot know the initial conditions with infinite precision, and in most of these cases the tiniest difference in the initial conditions, that is the starting state, leads to a huge or a large eventual differences in certain outcomes. And this leads to what we call is a chaos. I would like to conclude today's video with this, what we call is a butterfly effect. And it tells that in chaos theory, the butterfly effect is a sensitive dependence on initial conditions in which a smaller change in one state of a deterministic nonlinear system can actually result into a large difference in later states. And that is why it is told that if a butterfly flaps its wings, it causes a typhoon in some other country. And that is why this beautiful statement of none other than Paul Dirac tells that pick a flower on earth and you move the farthest star. In the delicate dance of existence, behold the poetic reverie encapsulated in this phrase. Envision a cosmos woven together by threads of connection, where the tender act of plucking a flower transcends the terrestrial realm, resonating the cosmic vibrations. Within the petals of a solitary bloom lies the power to stir the celestial tapestry. This phrase, like an ethereal whisper, suggests that our seemingly insignificant deeds possesses a profound ability to reverberate across the vast expanse of the universe. Imagined in the act of cradling a bloom, we unwittingly reach out to touch the fabric of the cosmos. Each petal, a note in cosmic symphony, vibrates through space and time, resonating with the distant twinkle of the farthest star. The interconnected dance of creation unfolds as the essence of a flower's fragility echoes through the cosmic bullet. So this is the time that we can do a quick summary. We learned a lot of things, so here is a quick summary of this. What is classical physics? We understood the true nature. We also understood the concept of Laplace's demon. What is quantum entanglement, the local and the non-local theory, spontaneous emission, reversible and non-reversible system, what is a system, what is not a system. We also learned what is a deterministic and a reversible system, isolated system, which is something analogous to linearized gravity, dynamical system and different space of states, irreversible and reversible system, dynamical system with infinite number of states, how the cycles are responsible for giving rise to conservation of laws, and how we humans are still have limitation in terms of measurement. So I know it has been a little bit longer video, but I think this is a deep philosophical understanding of classical physics. Do let me know how do you like about this video in the comment box, and do let me know your reactions also. Physics for Students will be back very soon with more surprising videos, but till then, goodbye, do take care, and do not forget to subscribe and click on the bell icon to get all the notification from Physics for Students. Thank you very much for watching this video.